So next we have number 4, where we have to prove that if we add a multiple of a row of one determinant to another row, then the value of the determinant does not change. So we start the solution by considering this general n by n determinant, where you already know the notation, but still let's say what it is. D of v1 v2, like that it goes, and we have also written in the middle somewhere we have vi and vj, where they are different. Okay, I and j are different, and in fact j is greater than I, because it's understood, so I have not written that. But these vk's are all rows. Each row has n entries, and this actually is the determinant of that matrix whose first row is v1, second row is v2, and so on. The nth row is vn, and each row is a row having n entries. So this becomes the determinant of an n by n matrix. So that's what the notation is. And we are considering here vi and vj because we are now going to consider the other determinant which we obtain from this one by adding a scalar multiple of vj to vi, and that scalar of course would come from the underlying field. In fact, the elements in these rows, the entries themselves, come from the underlying field, whatever it is. So we do just that. We consider this determinant obtained from this one by adding lambda times the jth row, that is vj, to the ith row vi, obtaining this new ith row. Okay, the other rows are the same. And you also see that I have mentioned these lemmas. We are going to use 3 lemmas here, which we already saw before, and they are 692, 693 and 694. First of all, lemma 692 allows us to write this determinant as the sum of these 2 determinants, where we keep all the rows intact except this row, which we can split into 2 parts, one having vi and the other one having lambda times vj. So 692 allows us to do that. Then in the next line we can take this lambda outside. You recall the statement of lemma 693, which tells you that if in a determinant you encounter a row which is a multiple of some fixed scalar, then that scalar can be taken outside. So that allows us to take this lambda outside from this row. Note that although you see here vj, but actually this is the ith position. Alright, and then what do we do next? And finally we use lemma 694, which tells us that a determinant is 0 if 2 of its rows are identical, and that is what we see here in the second determinant. The ith row is vj and the jth row is also vj, so that's why that is 0, and this is what we are left with. That means this determinant is equal to this determinant, or the same thing, this is equal to this. So what did we do to this determinant to get to this? We added the multiple lambda times vj of the jth row to the ith row, but that did not make any difference. The value of the determinant remains the same. Now in order to better see it, because this is somewhat theoretical, let's take an example and see these things in that example. For simplicity, we take this very simple determinant, a 2 by 2 determinant, where the entries are, say, real numbers, 1, 3, minus 1 and 2. Say this is our determinant, which is this. So we first calculate the value of this determinant, which you already know how to do. 1 times 2 minus 3 times minus 1, which is 5. Now say I change the determinant. What I do, I add to the first row 3 times the second row. Alright, this just like we added lambda times the jth row to the ith row in the general case, here we are adding 3 times the second row to the first row. That means 3 times minus 1 plus 1 and 3 times 2 plus 3. Alright, so this is our new determinant, and that general calculation we started with this one. And then we somehow showed that this is equal to this. So let's go through those same steps and see in this case how we got to this from that one, which you do not see here anymore. So first you do the split according to this row that has got affected due to this operation. That means we have added 3 times the second row to the first row, means the first row has been affected. So we are using the first row to do this split, where 1 and 3 go to one determinant and the other things 3 times minus 1 and 3 times 2 go to the other determinant. And then in the next step we take this lambda outside, because the first row is a multiple of this lambda, which in our case is 3. So by one of those results you can take 3 outside, and when you do, you get this other determinant where that Vj and Vj are equal. That means these two rows are equal. So by that other result, this determinant is 0, which in this case you can actually just simply calculate. And that's how we get our lambda back. So this is how the general proof went. But let's do one more thing here. We calculated this value and we found it to be 5, right? Let us really calculate this one. I mean, let's go through the calculation. Let's not rely on these results or anything to see that this will also be equal to 5. If you simplify the entries in the first row, here you are getting minus 2, because 1 minus 3 is minus 2, and here you get 3 plus 6, that is 9. And now you apply the formula for the expansion of this determinant, minus 2 times 2 minus 9 times minus 1. Here you are getting plus 9 and here you are getting minus 4. 9 minus 4 is 5. So it's matching.